Hi Bobcats. In this video, we're going to look at the Henderson-Hasselbalch equation for calculating the pH of a buffer. So our main objective is to apply the Henderson-Hasselbalch equation to get that pH of a buffer. So here is one form of the Henderson-Hasselbalch equation. pH is equal to pKa plus the log of the concentration of your conjugate base over your conjugate acid. Now let's get a couple of these terms straight right from the beginning. Remember that a buffer solution is composed of a weak acid and its conjugate base, or a weak base, oh whoops, I left off the word acid, or a weak base and its conjugate acid. So we are going to have a conjugate acid-base pair here, two species that differ by one proton. So when we're talking about pKa in this equation, that will be Ka for the acid form, the conjugate acid of your weak base, or the weak acid if we have a weak acid with its conjugate base. And then when we're looking at this ratio of the conjugate base over the conjugate acid, that is for the two pieces in this pair. That gets confusing in some of the problems that we will do because there is, in addition to the buffer, there will be added acid or added base, and that's not what goes into this equation. What goes into this equation is only information about your conjugate pair. And so if you are doing a problem where the buffer is made from a weak base and its conjugate acid, one of the steps that you'll need to take most likely is to calculate Ka for the conjugate acid. And so typically what will happen in those scenarios is that Ka will be equal to Kw divided by Kb for the weak base. So just remember, all of this stuff in this equation applies to your conjugate acid-base pair, and that really is the Ka. So if you were given the Kb, you'll have to calculate Ka from Kb. All right, now that I've gone through all that song and dance, let me give you a warning. This equation takes a variety of forms, and so you want to be really careful if you're watching tutorial videos that come from other sources, because they may be using a different form of this equation. When I took general chemistry, the form of the equation that I used had a negative sign in the middle of it. It is mathematically absolutely equivalent to the equation that we have here, but the conjugate base, conjugate acid term was inverted, and it's just a property of logs that if you're going to flip that ratio, you're going to change the sign on the log. And that's just how it was presented in the textbook we used in that class. And if you thumb through a variety of general chemistry textbooks, you will see this equation presented a number of different ways. So be very, very careful if you're looking at tutorials from other sources, because this equation may look really different. And you also can always use an ice chart to calculate a buffer pH, but I think that you'll find the Henderson-Hasselbalch equation is usually faster, and it's actually very helpful if you discover that you're solving a series of pH questions about the same solution with slightly different variations. The Henderson-Hasselbalch equation will usually be much faster. All right, so let's find the pH of a buffer. And in this first one, we're asked to find the pH of this buffer system using an ice chart. Now, this problem was very nice in that it actually threw the word buffer into the problem. It says calculate the pH of a buffer composed of 0.12 molar benzoic acid and 0.2 molar sodium benzoate. A lot of times the problem will just say calculate the pH of a solution that contains 0.12 molar benzoic acid and 0.2 molar sodium benzoate. You have to recognize that this is a buffer. It doesn't actually tell you that. But okay, let's do this with an ice chart. So let's look at our weak electrolyte. Our weak electrolyte is benzoic acid, so I'm going to call that HA. And that will be in equilibrium with H plus A minus. We'll have a change in an equilibrium. Initially, our weak acid is 0.12 molar. Our H plus is 0, and our A minus is 0.20 molar. To reach equilibrium, this has to go to the right, so we'll have minus X, and plus X. And so then if we add those two lines together, we'll have 0.12 minus X, and 0.2 plus X. If we look at our Ka expression, then we will have up in the top H plus times A minus, all divided by HA. And I just realized I didn't look up the Ka for benzoic acid. Fortunately, I have a table of Kas close at hand, and it is 6.3 times 10 to the minus 5 according to this table. So Ka is 6.3 times 10 to the minus 5, and that'll be equal to X times 0.2 plus X divided by 0.12 minus X. Okay, here's where we're going to make our assumption. I'm going to write it out up top so that I've got enough room to write it all. We are going to assume that X is small compared to 0.12. And then that means that X minus 0.1, other way around, 0.12 minus X is essentially equal to 0.12. Now, if X is small compared to 0.12, it's still going to be small compared to 0.2. So 0.2 minus X would be about 0.2. So we can make those substitutions in here. We're going to have 6.3 times 10 to the minus 5 is equal to X times 0.2 divided by 0.12. Now that X that we substituted in for H plus ion is multiplied. So we're not adding or subtracting something to it, so that we can't say that X is small compared to that thing we're adding or subtracting it to. We're stuck with it. That X has to stay. Now to get X by itself, we'll multiply both sides of the equation by 0.12 and divide by 0.2. So in my calculator, I'm going to type in 6.3 EE negative 5 times 0.12 and divided by 0.2. And let me get that into scientific notation. I'm going to get a value for X of 3.8 times 10 to the negative 5. Okay, X represents hydrogen ion at equilibrium. So in order to get the pH, we can just take minus the log of X. So that'll be minus the log of 3.8 times 10 to the minus 5. So let's see, we'll take log and change the sign, and we get a pH of 4.42. So the pH of this solution, according to our ice chart, is going to be 4.42. Now in the next slide, we're going to try to find this pH using the Henderson-Hasselbalch equation, and we should get the same value. All right, on this slide, we're going to try to use that Henderson-Hasselbalch equation, and we should end up with the same value. And I've already forgotten what it was we looked up for the benzoic acid, Ka. All right, 6.3 times 10 to the minus 5. And that's according to my table of Kas. So according to the Henderson-Hasselbalch equation, pH is equal to pKa plus the log of the base form divided by the acid form. All right, in this case, the benzoic acid is the acid form and the sodium benzoate is the base form, because the benzoate is that conjugate base. So this is going to be our A minus, this is going to be our HA. So if we plug numbers in, pKa will be minus the log of Ka, which is 6.3 times 10 to the negative 5, and then plus the log of the base form. The base form is 0.2 molar, and the acid form is 0.12 molar. Okay, now I usually prefer to run equations like this through my calculator in one fell swoop. But with the Henderson-Hasselbalch equation, especially if you're going to work more than one problem involving this particular buffer system, you're going to have to take that minus log over and over again. And so I just go ahead and do this in steps. I'll take the minus log of 6.3 times 10 to the minus 5 and write that down. That is going to be 4.20. And then I'm going to add to that whatever I get for the log of 0.2 divided by 0.12. So let 0.2 divided by 0.12 equals, and now take the log of that. And the log of that is 0.22. And so 4.20 plus 0.22 will be 4.42. So the pH of the solution calculated with the Henderson-Hasselbalch equation matches what we just found for the pH of the solution using an ice chart. So hopefully I convinced you that the Henderson-Hasselbalch equation is a good way to go. Our objective was to use the Henderson-Hasselbalch equation to calculate the pH of a buffer, and we did that for the benzoic acid sodium benzoate buffer.